Chapter 7 is actually going to be broken into two different sections. We're going to cover section 1 and 2, dealing with chemical names and formulas and oxidation numbers. After that, we'll have an exam, and sections 3 and 4 of chapter 7 we'll cover in a separate unit, and we'll have a separate exam on sections 3 and 4. Let's first begin off with a review of some similarities and differences between ionic and molecular compounds. First of all, let's talk about the bonding, what's going on with the bonding. For example, ionic compounds are going to have atoms that will gain electrons, some will have atoms that are going to lose electrons. For example, metals are going to lose electrons to form what we call cations. Nonmetals are looking to gain electrons and form anions. Now, the reason these atoms want to gain and lose electrons is so that they can be, just like their heroes, the noble gases. And when these oppositely charged ions become attracted to one another, that forms what we call our ionic bond. Now, unlike molecular compounds where we have atoms that want to share electrons to achieve a noble gas formation and satisfy the octet rule. When we're looking at the types of elements in these two bonds, remember ionic composed of metals and nonmetals. Molecular, we primarily see nonmetals. Now just remember there are some exceptions in chemistry. We will encounter some ionic compounds that will be made up of mostly or nearly all nonmetals. There are molecules that could possibly have a metal atom attached somewhere on its molecule. So remember that that's just a general guideline. When we're looking at their structure, remember an ionic compound, the formula unit shows a simplest ratio between atoms in that compound. It's an infinite size structure, three-dimensional array. For example, when we're looking here at sodium chloride, okay, we're going to see this three-dimensional structure here. And when I look at the ratio of the green to the purple atoms in this ionic bond, we're going to see a simple ratio like maybe 1 to 1. Unlike a molecule, where its two atoms bond to form a finite structure. For example, if I wanted more water, I would just keep building molecules composed of 2 hydrogens and 1 oxygen. When we're looking at their states, ionic compounds are mostly solids that have very high melting points. For example, salt, for example. If I tried to melt sodium chloride, I wouldn't melt sodium chloride until I achieved a temperature well over 800 degrees Celsius. So when we're talking about high melting points, we're talking about things that melt over 300 degrees Celsius. When we're looking at nonmetals, a lot of those are mostly liquids and gases. And when we're looking at their melting and boiling points, they're very low. There's some alcohols that could actually boil in the palm of your hand. Your body temperature is enough to cause them to boil. So there's lots of differences between these compounds, but there are some similarities. If we look at the similarities, they are both composed of at least 2 kinds of atoms. They're held together by a chemical bond. And if I wanted to separate them, or separate the atoms, I would have to use some sort of chemical means to separate the atoms. In an ionic compound, I'd have to use a chemical means to separate atoms in a molecular compound. Chemical formulas. When I look at a chemical formula, it shows us the kinds and number of atoms in the smallest representative unit of the substance. And depending on the type of substance I'm dealing with, that's going to define my representative unit. For example, ionic compounds. The representative unit for an ionic compound is referred to as a formula unit. And that tells us the lowest whole number ratio of atoms. For example, if I look at the diagram of the sodium chloride model, we see sodium ions represented as pink, purplish colored ions, and the chlorine as the green ions. And looking at that structure of sodium chloride, it looks like there is a lot of ions there. But since this is ionic, I'm not going to count the number of ions of sodium and chlorine. I'm just going to look for the ratio that exists between them. Because it doesn't matter what size piece of salt I have, I'm going to always see a ratio of 1 sodium for every 1 chlorine. And that's referred to as a formula unit. Unlike a molecular compound, which we have a molecular formula. A molecular formula is going to tell us the kind and number of atoms in a single molecule of this compound. Now, a molecular formula doesn't tell us anything about its structure. For example, if I asked all of you to draw me a Lewis structure for C4H10, 4 carbons and 10 hydrogens, there's actually 2 different ways that I can put these atoms together. You can see in the diagram. One way, I can see all my carbons are sort of lined up in a row, and my other structure, I have 3 carbons in a row and I have 1 branch. Okay? In molecular compounds, we have something called isomers. And these would be 2 isomers of butane. It tells us nothing about its structure and its molecular formula. Okay, if I wanted to know how they're put together, I would have to use something called a structural formula, and that's a topic for another lesson. Let's not forget about our diatomic elements. We have 7 of them, and these elements exist in nature in pairs. And when we look at the bonding that occurs between these atoms, we see single bonds. For example, the hydrogen, the fluorine, chlorine, bromine, and iodine all have a single bond, whereas oxygen has a double bond, and nitrogen has one of the strongest bonds of all, a triple bond. And when we write formulas for these elements, they include subscripts. For example, if I were writing a formula for elemental hydrogen, I'd write H2. If I would write a formula for elemental oxygen, I would write O2. I include a subscript. Just some other interesting tidbits. These elements aren't the only elements that sometimes have subscripts. For example, phosphorus and sulfur also exist in a state where it has subscripts, where the atoms are actually sort of bonded together. The black visual on the slide shows an example of sulfur. Sulfur in its nice, pretty yellow form is referred to as sulfur S8, an 8-membered ring. If I take that yellow powder and I heat it, and we could do that, but it would stink up the room pretty good, and I would heat it until the point where it started to turn brown and it would become very molten. And if I would immediately pour that into some cold water, it would result in something called plastic sulfur, which is sort of a 16-membered ring, much more flexible and stretchy. Another one is phosphorus. Now you'll find this one probably a little more exciting. Phosphorus, the white form, is a P4 molecule, and very, very unstable. It's very unstable in normal conditions, and it will gradually sort of change over to red phosphorus, sort of all by itself. White phosphorus, very dangerous to handle, because when it's exposed to air, it actually self-ignites. The next slide will show you an example where phosphorus, this white phosphorus, has been dissolved in something called carbon disulfide. And when the carbon disulfide evaporates, it's going to leave the white phosphorus behind and it'll self-ignite. White phosphorus won't dissolve in water, but it will dissolve in a substance called carbon disulfide.
White phosphorus dissolved in carbon disulfide is taken into a medicine dropper and used to write on a piece of filter paper. The pale yellow color of the white phosphorus can be clearly seen on the paper as the writing is done. As the solvent carbon disulfide evaporates away, the phosphorus begins to react with oxygen from the air. The spontaneous combustion reaction is an exothermic one that causes the paper to char, leaving P4, the formula for white phosphorus, burned into the piece of filter paper.
It's going to become increasingly important in this section to remember the patterns that we see with our main group elements. Group numbers let us know how many valence electrons that particular atom in that group has. For example, all the elements in group 2A would have 2 valence electrons. All the elements in group 6A would have 6 valence electrons. And in order to satisfy the octet rule, elements are going to either gain or lose electrons. Now, if I'm looking at a metal in groups 1, 2, or 3A, metals tend to lose their valence electrons. And in that process of losing that valence electron, the resulting particle, an ion, is going to acquire a positive charge. So, for example, magnesium has 2 valence electrons because it's in group 2A, will lose those 2 electrons when it becomes an ion and acquires a 2+ charge. On the other hand, if I look at oxygen, I know oxygen has 6 valence electrons, and it wants to gain 2 more in order to have 8. So when it gains 2 electrons, and it could gain the 2 that magnesium gave up, it's going to acquire a -2 charge. The same thing with anything in group 7A. They have 7 valence electrons. They want to acquire 1 more electron so they can be like the noble gases. Now when we're looking at naming these ions, metal ions are referred to as cations, and their name stays the same. So when I'm naming cations, I would just call this a magnesium ion. However, when I'm naming anions, we're going to see a little bit different in the naming. The name is going to actually change. So, for example, oxygen, when it becomes an ion, we're not going to call it an oxygen ion. The name is going to change to oxide. So the ending is going to become IDE. So anytime that we're naming an anion, which would be anything in groups 5, 6, or 7A, the ending is going to become an IDE ending. Now when we look at the transition metals, or the D block elements, we see a little different situation with these elements. These elements can actually form multiple ions, okay, which means that they may lose a varying number of electrons. And for example, copper. If I have my book open to page 221, you can see some examples. And if I look at copper, I can see, according to this chart, copper can actually form a +1 ion or a 2+ ion, which means that depending on the situation copper's in, it may lose 1 or 2 electrons. Now when we're naming these cations, they use what they call a stock system, which is going to use Roman numerals. So when I'm looking at a transition metal or a D block element that has more than 1 charge, I'm going to use a Roman numeral when naming that particular ion. Copper is very common. Another common one is iron, can form multiple ions, but there are some D-block elements that don't have multiple ions. A common example would be zinc. If I look at zinc, zinc can form a 2+ ion. However, I don't use a Roman numeral for zinc's name. Silver is another common example. Silver will lose 1 electron, form a positive charged ion, and I will not use a Roman numeral in that particular element. And those are things that you're just going to have to remember. The fact that zinc and silver don't need Roman numerals. But there are some common ones there that we need to definitely know they need Roman numerals. Iron and copper are definites. Tin, lead, and we'll go over those again at the beginning of the week. Let's go ahead and let's open your book on page 226 so we can talk a little bit about polyatomic ions. Polyatomic ions are a covalently bound group of atoms, behave as a unit, and they carry a charge. Most of these ions are also called oxyanions because of the fact that most of them contain oxygen atoms. Now, when we glance over at the names of these particular ions, I have a sampling of ions on the slide. You can also look on page 226. When I look at the names of these ions, we should notice a pattern or some similarities. And the pattern or similarity that hopefully you've noticed here is the fact that most of these ions end in either ATE or ITE. Now, we notice there are a few exceptions. For example, a common ion is hydroxide, OH, and cyanide. They don't end in ate or ite. They actually end in IDE, but they're still polyatomic ions. Now, let's just take a look at, for example, chlorate and chlorite. Look at the name. Let's look at the formula. Now, let's go over and look at, under the 2- charge column, let's look at sulfate and sulfite. What are we noticing about this name and a relationship with the number of oxygens? Hopefully you've noticed that the ending with ATE has more oxygen atoms than a name with the ending of ITE. So if I'm over under the column that says a 3- charge, there's a formula for phosphate, PO4 with a 3- charge. Can you guess the name of the PO3 with the 3- charge? Hopefully you've guessed phosphite and you would be correct. So the ending, ate and ite, not only tell us that we're dealing with a polyatomic ion, it also tells us a relationship with the number of oxygens. Now there's some other naming systems here we need to look at with these polyatomic ions. Now let's take a look at some of the prefixes. And we're going to go back to the chlorine family under the 1- charge column, where we see perchlorate, chlorate, chlorite, and hypochlorite. Now if you notice that each of these ions contain chlorine and oxygen, and the only difference between them is the fact that they have different amounts of oxygen atoms. We already looked at the chlorate and the chlorite relationship. Now, when I see that prefix per on the front, perchlorate, notice I have one more oxygen. Look over in the the 2- charge column. We see something called peroxide. Okay, oxide would be O with a 2- charge. Peroxide, an extra oxygen, O2 with a 2- charge. So per is a prefix that we see that means extra. Now, in a lot of cases, it's meaning an extra oxygen. And back to the chlorine family. Notice that we have a prefix hypo. Hypo is something meaning less. So if I look at chlorite and I compare it to hypochlorite, we notice that there is one less oxygen atom. So hypo is another prefix that we see that means less, if I look at that relationship in the chlorine family. Another common prefix we see is the prefix bi. Well, a lot of times we like to think of bicycle, bicentennial, the number 2. It's not the case in chemistry. In chemistry, bi actually indicates hydrogen. So if I look at the 1 minus charge column, I see something like hydrogen carbonate. CO3 is carbonate. Put a hydrogen in the front, I'm calling it hydrogen carbonate. But I can also call it bicarbonate. How many of you have heard of sodium bicarbonate? That's baking soda, which can also be called sodium hydrogen carbonate. So bi is a prefix that means hydrogen. Another prefix that we see is a prefix thio. Now, thio is a prefix that indicates there's some sulfur, or maybe an oxygen has been replaced with a sulfur. So thio, we notice that we see there's a thiosulfate ion, and in the bottom of the 1 minus column we see a thiocyanate, SCN. We've got that cyanide ion, and now we're adding a sulfur. So thio is a prefix that indicates sulfur. Let's take a look at, in the 1 minus charge column, we see underneath cyanide, we see an ion called dihydrogen phosphate. And if you look at the 2 minus column, almost right beside it, we see something called hydrogen phosphate. Can you guess what the prefix di means? Well, hopefully you guessed 2, because di does mean 2 in chemistry. For example, a common compound, carbon dioxide. We know carbon dioxide's formula is CO2, di meaning 2 oxygens. So I would become familiar with this naming system with polyatomic ions. You do not need to memorize them. Of course, though, after repetitive use, some of these you're just going to know off the top of your head eventually anyway. But on the back of the photocopied periodic table, I always have a chart of polyatomic ions on the back. So just become familiar with them, become familiar with their nomenclature, the prefixes and the suffixes. But you do not need to create a memorization chart of these. So hopefully by the end of this slideshow presentation, you've become a little more familiar with ions, how they're formed and how they're named. And we will be going into actually naming compounds in the next lesson.